Okay, hello everyone. So today it was a strange day with internet connection. I know many people experience problems. Actually, I should drive from my home to my office to start it, but I'm lucky we can have a lecture today. So let me start recording and let me start sharing my screen with you. Okay, so as you know, we end up with exam 2. We start chapter 6, and even we did not have synchronized lecture last week. I hope you attended the lecture. I hope you heard what I recorded, what I posted, because it's really important. We start new topic, we start second law, right? So I recall what we did. Actually what we did is I sent you homework number 6, right? It was posted last night, and we should be prompt because it's due next Wednesday next week. It's November 11th. The homework is not big, and I do believe if you proceed well today and on Friday, this weekend you should be able to work on it. Help session as usual will be 2 business days prior to that homework. It will be Monday and Tuesday. Please attend it. And why we are so prompt? Because after this, I will give you homework number 7A. It will be first part of entropy class. Because in fact, almost in 2 weeks, you have your exam 3, right? It will be November 20th. We should have it because we have only several weeks left before Thanksgiving and only 1 week after this. Anyway, we are at second law, and I know this time, this homework, we spend a lot of time of theoretical and philosophical questions, but it's important. I do want you to understand what second law is, how it looks like, because first it looks like not very nice, not very convenient. But if you understand it, if you will be able to dive deeply in this, everything will be easy and self-consistent. Please realize it, okay? So that we started. Last time we introduced second law, and I told you there are many ways how you can deal with it. Please realize second law is something in between juridical and physical law, right? It's something that you may not but won't violate. And I tell you how you can consider it. This law has never been proved, right? It has never been proved experimentally or theoretically, but you know it exists. It's empirical fact, and you know if it would not work, nothing we talk about here would not work in that case. So that's you may believe in it. And I told you how you can consider it. That when you are young, when you are children, people tell you don't do something and you don't do. And ancient Greeks, whom I recall all the time, assumed that you cannot do something that gods or nature does not want to do. They assume that you cannot do what power cycle and refrigeration cycle do. They assume that you cannot convert heat into work. They assume that you cannot convert transfer heat from cold to hot source. They assume it's prohibited. That's a law. But when you grew up, how our civilization grew up, you say, okay, I want to violate this. That's what nature desires, but I do want to do something that is not desired by the nature. People say, we do want to convert heat into work. We do want to transfer heat from cold to hot source, right? We do want this. And actually all our thermodynamics, all our industry and manufacturing is based on this. We say, we want this. And nature replied, okay, but if you want to do this, this will be irreversible. Because you will never go back. It will be step towards thermal death of universe. If you do something, you should pay for this. You should be penalized. And second law tell you what penalty you pay, how you pay, and currency in which you pay this penalty is entropy, which we'll be talking in chapter 7. Does it make sense? It's my interpretation of second law that I want you to understand. You cannot violate second law, but second law tells you what penalty you pay against nature. Because nature does not want to do something. When you have a piece of sugar and you want to drink a sweet tea, you dissolve this sugar in a tea and you cannot get it back. It's irreversible. You should pay penalty for this. And even ancient Greeks did not know thermodynamics. They knew what I'm talking about. It was philosopher Heraclitus who told that everything which is born should die. Why? Because when you are born, when animal is born, when plant is born, you violate the order. You introduce something new in your universe which want to be clear and clean. And you should be penalized for this. That's why you should die. You should first born and then die, not vice versa. It's process in one direction. So what is this unless it's second law? It's second law of thermodynamics, right? Does it make sense? Do you understand this? So all the process we talk about typically go in one direction. And many devices we considered in chapter 4 and 5, like turbines, compressors. I gave you state 1, I gave you state 2, I asked you to find them and say, please find work output, and you did it. I never ask you, does this turbine exist or not? And now you may check this, and you will see after this chapter that it sometimes may not exist. That's important. Any question about this at this point? Do you understand this? I hope so. Okay, let me continue. So do you see my screen, I believe? So we so far considered two statements of second law and demonstrated their equivalence, right? What are these statements? What we did last time. We introduced what concept we talk about. We discussed different aspects. We say that second law works only together with first law, right? If first law does not work, second law does not work too, and there is no reason to consider it. And in your homework, there is problem number 3, when you should check first law and second law. Please realize, if there is no energy balance, second law can give you anything, no reason to consider it. So second law is supplementary to first law, like this chain. And what we considered? We say that there is Kelvin-Plank statement. What is state? It states that it is impossible for any system to operate in such a manner that it operates in thermodynamic cycle that it deliver net amount of energy by work to its surrounding while receiving energy by heat transfer from a single thermal reservoir. So otherwise, it is impossible to have heat engine operating with one thermal reservoir, right? You cannot convert this heat entirely into work. It should be another thermal reservoir here which will reject heat. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surrounding while receiving energy by heat from a single reservoir. Otherwise, it states that heat engine cannot operate like this. To be more specific, heat engine should have a second reservoir, right? And remember what is heat engine? Heat engine is device which deals with energy heat conversion into work. You know that I can convert work into heat directly. It's easy. Ancient Greeks knew this. But when I try to do vice versa, I can do it. But I should have another reservoir and I will lose something here. That's second law. And we considered also another statement. How we call it? We call it Clausius statement. Clausius statement talk about fridge. It says the following: it is impossible for any system to operate in such a way that the sole result would be energy transfer by heat from a colder to a hotter body. Correct? What I'm doing here? Okay. Sorry, guys. Yeah. Again, please don't say that it's impossible to transfer heat from cold to hot source. It's possible. Your fridge does it, isn't it? But it is impossible to do it for free. It is impossible to have systems that when heat goes directly from here, from down to up, and nothing else happens. Vice versa, it's okay. Vice versa, heat goes from hot to cold source, it goes to equilibrium, but not vice versa. You have some imposition of work, and that is Clausius statement. Otherwise, it states that if you have refrigeration cycle or heat pump cycle, if you have a fridge, your fridge does not work for free. Your fridge needs power supply. Do you understand this? It's impossible to be like this. Do you understand what I'm talking about? No questions yet at this point? I hope so. Now, no questions? Okay, very well. At this point, let me do the following. So let me briefly recall what are thermodynamic cycles and what cycles we are considering. Because we actually started talking about cycles in chapter 2, right? We say that what is a cycle? It's when you start from one point and go through other properties and come back to the same state, right? It's a cycle. And we considered what we do in thermodynamics. Like I say, we do two things that ancient Greeks did not know. We consider power cycles. What is power cycle? It's heat engine. It's device which convert heat into work with some losses. And we consider refrigeration and heat pump cycles, which actually do the same. They are conceptually different from the goal, but they do exactly the same. They transfer heat from cold to hot source, and they take some penalty from you for this, some effort, some external power. So what is power cycle? How it typically looks like? So it states here that you should have two reservoirs. You should have hot body, you should have cold body, right? And heat goes from here to here. So Q in, Q out goes here, and difference between them is converted into work. And what second law gives you, what Kelvin-Plank statement gives you, it says that you must have this second reservoir, right? Here, work of a cycle will be net energy transfer by work. Q in what goes in, Q out what goes out. Does it make sense? Any question about this? And energy conservation look like here, like you see on the screen now. That is your energy conservation, right? Now, so that will be your energy conservation. And if you do a cycle, delta E of a cycle will go out. So this will be work of a cycle will be Q in minus Q out. It's still energy conservation. Now, in this device, remember we talk about thermal efficiency. What is thermal efficiency? What is efficiency coefficient? How we determine it? Is desired over required, right? Take what you desire, divide by what you require. You desire to eat apple, you require apple in envelope. So take desired over required. So if you talk about power cycle, what do you desire? You desire work done over cycle, correct? What do you require for this? You require heat input. The ratio it's at, right? So basically that's what you see here. These are the basic equations that you see. Well, last equation is just transformation, but that's what you have. That is your equation. And what do you know about value eta? From chapter 2, you remember that this value eta is what? It's larger than 0 and it was less than 1, correct? And we knew this. Because definitely you cannot produce more energy that you consume. You cannot generate energy. But now what do we know? We know that you must have Q out. You must have this value, right? Why do you need to have it? Because of second law. So actually what you will see now that your value eta will be less than some maximal value, which will be smaller, sorry, than the some maximal value, which in turn will be less than 1. Why? Because of second law. So now you have more strict statement. It's not like it cannot be 100%. There is some limitation. You need to have Q out. You need to have your second reservoir. Do you understand this? Why do you need to have the second reservoir? Why do you need to have Q out? Some naive people tell, okay, because our systems are not ideal, because you have friction, because you have dissipation, because you have heat losses, because I cannot make 100% isolation. No. All these items have, not because of this. Assume you may do 100% of isolation. Assume you can avoid friction dissipation. Assume you have theoretically best system. Still, you will have this Q out because of second law. Because it's impossible theoretically to have one reservoir. You need to lose something. That is a penalty you pay to nature. If Q out would be 0, there would be no Big Bang, and our planet would never appear. And our galaxy would never appear. So you may believe it's true. Okay? Does it make sense? Now, so that's what we considered. And that's how Kelvin-Planck statement looks like, that you need to have another reservoir. For example, if you have power cycle, so let's say, let's read this problem, for instance. Let's say you have system which undergoes a power cycle, and this system receives 100 kilojoules from hot reservoir and discharges 600 kilojoule to cold reservoir. So the question is, please find that what is network developed and thermal efficiency, right? So how we should proceed with this? So what we have here, basically that's what you have, right? You have two reservoirs. I can plot it here. You have hot reservoir with temperature TH, which is what? Which is 500 Kelvin. And you have cold reservoir with temperature TL, which is 300 Kelvin, right? And you have heat engine between them. That is scheme that people will be asked to draw. So what happened? From TH here you have Q in, or let's say QH, I can call it QH, I can call Q in, right? What is this? It's 1000 kilojoules here. That's what I get here. And it is stated that it will be converted into work output. Okay? But what you know, you must have this reservoir. It's something here will be lost. So here something will, amount of QL will be lost. Do you understand? Do you understand this? Because of second law. And what equation I can write down here? I have two equations. One equation, I have that QH minus QL. Here I talk about positive values. It will be work out, right? And I have second equation, which I will say that my thermal efficiency will be what? Will be work out divided by QH. Okay? So how many equations do I have here? I have two equations. How many variables I have here? I have four variables. This one, this one, this one, and this one. So basically you need to know two of them to find other two. Okay? You ask me, why do I talk about temperature here? Okay, we will fix this on Friday. Now that's what you need to know. So to describe, you need to know two items to clarify two other of them from here. Does it make sense? So in your particular case here, what will be? Here you will say that work over cycle will be QH minus QL. It will be 400 kilojoules. And thermal efficiency will be this work over cycle divided by total heat. It will be 40%. Does it make sense? Do you understand this point? Do you understand this? That's what you need to know. Sorry. Okay. So that's power cycle. And basically, if you look here, again, I show you the equations that you may see. So here, it's before this point, right? You have actually four sign equal, so you have two equations and four variables. That's what you need to find. Now, how it looks like. So basically, you may see here that basically a typical power plant looks like here. You have a turbine, right? You have a turbine, you have a condenser, you have pump, you have boiler. It may be different, but that's typically how it looks like. And you go here clockwise, right? You go clockwise because work output is positive. Remember, if cycle is clockwise, it's positive, if counterclockwise, is negative. That's what you have. What happened in turbine? You convert part of heat into work, and something else is rejected here, right? What happened in condenser? In condenser, vapor get condensed, so it means that latent energy of vapor is rejected to the environment, it goes out. What happened in pump? You put some effort to put it up. And what happened in the boiler? In the boiler, you get heat, Q in, which is converted eventually into work. How you get it? Because and how it goes? It goes into boiling. Instead of liquid phase, you will get here vapor phase. So it goes like this. So that it is. And if you remember chapter 5, what we did in chapter 5? In chapter 5, we managed to consider all these devices separately, right? That was your state I, that was your state E, or 1 or 2, inlet, exit. That was inlet, that was exit. That was inlet, that was exit. And you consider them separately. Now, what in addition, and you still should be able to do it. And is that what you are going to do in homework problem 5? But in addition to this, now you should zoom. Imagine you zoom it out and you consider this device like one box, right? Like one big box. So this one big box is what we call heat engine. So basically what I have here, I can write down it like this. Here I will have TH, and here I have my hot reservoir, right? And here I have, let me do like this. And here I will have my heat engine. And here I have my TL, my cold reservoir. So what happened here? Here my Q in goes in, right? It's boiler. Here is a boiler. Do you agree? Here is my boiler. What I have here? Here I have workout, right? And here I have my condenser, my Q goes out. Does it make sense? So it's like zoomed picture. This is like zoom out picture, zoom in picture. That's what you need to know about power plants. Do you understand this? Okay. Now, let's talk about refrigeration cycle. So refrigeration cycle and heat pump will be after this. It's something similar, right? And basically, yeah, and also should recall about power cycle that we considered in the class, and remember examples we considered last time. So basically that's what you consider in the class. Where is it? Yes, so we considered efficiencies, and there is a good example, 6.1, 6.2 in your textbook. You may see that if there is heat engine here, 100 kilojoule comes here, 20 kilojoule is rejected, 80 kilojoules goes into waste, into cold reservoir, you may easily find your efficiency. Here it will be what? It will be 20 over 100, it will be 20%. In second reservoir, you have, in second engine, you have what? 30 kilojoules is converted into work, 70 is rejected. So your efficiency will be 30%. It makes sense, right? So definitely the second heat engine is better than the first one. And still your theta is less than 1. That's what you remember. Now let's forget about this. Let's go into refrigeration cycle. I recall the purpose of refrigeration cycle is different. It does not convert heat into work. It transfers heat from cold to hot body. And it gets some tax for this, some money, some earning for this from you. It does not work for free. It cannot be like this. You need to deposit some work input. So as before, so what you should realize is, work over cycle, here it's actually, if you talk absolute value, it's okay, but basically from the point of view of refrigeration cycle, it will be negative. Please understand it. So Q in will be here and Q out will be out, right? So basically what you will have here, again, you may remember what I can write here, that I will write that Q out here will be what? Will be Q in, if I talk about absolute values, plus work over cycle, correct? Or it's here. So that's your energy conservation. That's your first law. It should work. If first law does not work, no reason to talk about anything else. And now we talk about coefficient of performance. No, we don't talk about efficiency, we talk about coefficient of performance. Why it's not efficiency? Because it may exceed 1. So what is the, but again, the definition is exactly the same. What is the definition? What do you desire and what you are required here? We will say that coefficient of performance, or we call it beta for refrigeration, It will be what? What do you desire from here? You desire which heat which goes from here. It will be what we call Q in or QL, because L sometimes or it's like lower temperature. And what you require? You require work over cycle, right? That will be a coefficient of performance. And please remember, this value can be less than 1, but it can be larger than 1, unlike theta. No problem, this value to be 5 or 10, because that is your coefficient of performance. Like I told you, look at this point. What is it? It's Q in over work over cycle. Imagine I ask you, bring 1 ton of material to 8th floor. You can do it if you have good elevator or good cart to bring it. Even your oven mass is 50 kilogram, right? You weigh 50 kilogram, but you can bring ton. So your coefficient of performance will be 1 ton divided by 50, which is 20 times, right? And it's okay. Do you understand? The only thing you should realize here and remember is the following, that this coefficient should not be infinity. This work over cycle, this work input should be finite. It cannot be 0. If it was 0, it will be infinite. Beta will be infinite, but according to second law, you must have it. Do you understand this? And that it is. So how a typical refrigeration cycle look like? So typically it's counterclockwise, right? It's counterclockwise as compared to power cycle. It's go vice versa, right? In this direction. So what does it mean? It means that work over the cycle will actually negative. From the point of view of your fridge, work is negative. Work is done externally on it. You see it? It's external work. Work over cycle will be negative. So basically that it is. And what you may see here, how it works typically. Typically, you get heat from your body of the fridge. How you typically get? By evaporator, because if you evaporate, heat goes from here. Then you have a compressor. It is compressor when you have electrical power to supply, or you can do it by hands, when you compress your item and you get high pressure. And then at high pressure, you have condensation. What is it? Condensation. It means that your vapor here, as this condenser, your vapor becomes, you get liquid phase. And then when you get liquid phase, heat is rejected into the environment. Remember, it's fully different from what we had for power cycle. Remember, for power cycle, here it was boiler and here it was condenser. Here it's vice versa. Heat goes up. And then you have expansion valve, which come back to initial state. And remember what expansion valve is doing. It is cooling. You can go from high temperature to lower temperature. Remember problem 8 from your homework 5 and from exam. So what is most important here to realize? You must have compressor. If there is no compressor, fridge would not exist. And that's fully in line with second law. You must deposit something into your system. Heat can go from here to here, but it cannot work for free. Again, all these devices we have here, it's like you did in chapter 5. You can consider them separately. This is state 1, this is state 2. This is state 1, this is state 2. This is state 1, this is state 2. This is state 1, this is state 2, and so on. So each of them can be solved separately. Identify state 1, state 2, and write first law for open system for each of them. But now you also should be able to zoom them out like we did before, and that becomes your refrigerator. So if you zoom it, the system looks like this. Here you have your cold reservoir. Again, you need to have 2 reservoirs or cold body from which you transfer heat. Here you have your hot reservoir. Here you have your refrigerator. You take heat from here, right? So what happens here? It's your evaporator. It's here. And you transfer eventually heat to your kitchen. What happens here? It's here, right? But you cannot do it for free. You will have some work input from here, which is not 0. Do you understand this? And your coefficient of performance will be what? Will be this value divided by this. That is what you want. Does it make sense? I hope so. Okay, and why we say it? Because that it is actually what you see here, that it was desired, that is what's required. Coefficient of performance, we call it beta, is desired over required. That's what I discussed a couple of times. But key point, if you see the difference between heat pump and this one, here what you need. At this problem, you don't care much about QH, right? You don't care much. You care about QL because you care about temperature in your fridge. You don't care about temperature in your kitchen. You care about this. That's how it works. And again, what if you see here, what you have here? You have two equations because you have two equality sign, and you have four variables. 1, 2, 3, and this is the coefficient of performance 4, right? And basically that is 3 of them, and you also work input is here, right? So you have two equations, 1, 2, 3, 4. You have two equations and two unknowns. Otherwise, you can also write it like QL over work input, right? So basically here you have what? You have four unknowns, and you have four variables, and you have two actual equations. You need two of them to know two others, QL, QH, and this value. Does it make sense for you? Do you understand this? You need to know two of them to find two others. Again, this value can be larger than 1, less than 1, but definitely it's positive. And again, Clausius statements say nothing but that there is no system. It is impossible for any system to operate in such a way that the only result would be energy transfer from cold to hot body. I encourage you in the exam, the key point here, the sole result, the only result. Don't say it's impossible. Don't say the statement without word sole. Don't say it's impossible to transfer for any system to operate in such a way that the result would be heat transfer from cold to hot source. That's wrong. Your fridge does it. Ancient Greeks assume it's correct, but we know it's wrong. But we know we should pay penalty according to second law. And that's really important. That's something that you must remember, right? Okay, very good point. Why do we use subscript H and L? Okay, and that's a good point because in different books you have different subscripts. I will tell you. So typically H, we use H, TH, because H means hot. You have hot reservoir, hot body. So subscript H means hot, and sometimes this Q which goes here, we will call it QH. Okay, it can be Q in, Q out, it will be QH. From cold body, so sometimes we call it Q out, but sometimes we call subscript TL. We also use subscript L, which means lower temperature. Or sometimes we use TC, C means cold. So it can be hot, it may be hot, and it may be hot, and it may be high temperature. That's why subscript H. And subscript L means low temperature, and subscript C means cold. For instance, in your classical textbooks, we use H and L, but in textbook by Moran and Shapiro, for instance, they use H and C. So I just wanted to realize it. Does it make sense? H means hot and high, L means low, C means cold. But you have two reservoirs. One is cold, one is hot. Okay, thank you. So that's a good question, really good. Now, so that is Clausius statement. Now, what is heat pump? Okay. Frankly speaking, sometimes in some textbooks don't distinguish heat pump from refrigeration because it does exactly the same. It's actually still the same refrigeration cycle. Heat pump takes heat from cold body, transfers to hot body, and by means of deposition of work input. That's work input here. It's like your card, which is helpful. You want to go we see this picture. You want to go from first floor to fifth. You need some effort, some elevator to help you to go. The only difference, the purpose of it. Refrigeration transfer heat from entire body of your fridge into kitchen, right? So the goal here is QL or Q in, right? Heat pump does the following. It takes heat, when it's winter time, like now, so it will be soon. It takes heat from the street and push it into your environment, into your apartment, into your housing, into your vessel, let's say like this. So now you don't care about your street. You don't care about cold reservoir. You care about your hot body. So now you care about Q, which goes inside. So for heat pump, what you desire is actually QH, or how we call it Q out. And now you may realize why I put QH, QL, because Q in and Q out, they're changing from power cycle to fridge cycle, but QH and QL have the same destinations. So basically, that it is. Heat pump does exactly the same. It can be the same device which works at heat pump, but coefficient of performance will be different. So again, the same story. For work over cycle, you have this equation, it will be energy conservation. But coefficient of performance for heat pump will be what? It will be Q out, QH divided by work over cycle. Do you understand this? I can also write it like here. It will be actually QH over QH minus QL. And that is important. Why it's important? That is really important. So because you may realize now that for fridge you had QL here, now you have QH. And this value is definitely larger than 1. We call it gamma. So for heat pump, coefficient of performance is definitely larger than 1. Because when I ask you to bring something to its flow, what you will bring to its flow will be what you pick up here plus yourself. This is definitely larger than you. Otherwise, you will just jump for free. But again, this value is not infinite. It should be finite because work over cycle is finite. So that's the difference. So please realize the mechanism of work is still the same. Because I tell you, in thermodynamics, there are two principles: converting heat into work and transferring from cold to hot source. But we distinguish heat pump and fridge because of goal, how they work. So basically, that's what you need. So that is for heat pump, and like refrigeration, that is what you desired, that is what you required. And that is the ratio. Okay? So basically, class the example, for instance, let's consider example, and you have actually similar example for refrigeration cycle and for heat pump in your text, let me see here. Yeah, in your textbook, you have example 6.3 and 6.4. They are good examples which shows you how to calculate efficiency. You can go through these examples, and the same in your homework. It will be problem 5 and 6 when you consider it. And when you consider heat pump, you should be able to zoom it out and consider it separately. That's problem 5 and 6 from your homework. So basically here it is. Let's see here. So for instance, I have working, let's say I have heat pump like this. I have QL, which takes 5 kilograms from outdoor, from the street. And my heat pump works in such a manner that it consumes 2 kilojoule, such that 7 kilojoule is delivered to my room, to my apartment. Okay? So the question is how it works. Definitely you have conservations that 5 plus 2 will give you 7. What will be coefficient of performance of this device? We consider what do you want from it? You want QH. What do you require? You require work input. What is the ratio? The ratio is 3.5. So coefficient of performance will be this one. While you may realize that if you talk about fridge, it will be this over this, it will be 2.5, it will be less. This is the ratio between efficiencies or coefficient of performance for heat pump and refrigeration cycle. Does it make sense for you? Do you understand? I hope so. So that is example. For instance, let's say you have a system which there is a heat pump, which it undergoes heat pump cycle. As the system discharge 900 kilojoules to your house and receive 600 kilojoules from the outside street. So basically what it is, if you plot it like this. Here is like your house, right? So your house here will be like your hot reservoir. It will have 20 degrees Celsius. And this will be your TH, right? And by the way, here I put in Celsius, but when you come to calculations, I do request you always use Kelvin. It's much more convenient and you will not do mistakes because there will be formulas. So what is stated that you have heat pump here, and it stated that this heat pump discharge 900 kilojoules here. So 900 kilojoules will be here. 900 kilojoules. That is what? That is your QH. Okay? It's 900 kilojoules. But how it comes here? Because it receives 600 kilojoules from the street. Here is your street. Here is your street. This is your environment. And here you have TL, which is 5 degrees Celsius, right? here you get QL from here. This QL will be 600 kilojoules. Okay, 600 kilojoules. The question is, determine the cycle, the network input, and the coefficient of performance. So what you will be doing? Yes? What you're going to do here? You will calculate what is work input. How to calculate it? Work input will be this minus this, right? Work input will be QH minus QL, correct? And you will calculate it. It will be 900 minus 600, it will be 300, correct? And what will be coefficient of performance? We call it gamma. It will be what you desire here. You desire 900 kilojoules. You require this work input, right? Here will be 900 and divide by 300. It will be QH over work input, and it will be 3. Does it make sense? You see now, instead of showing you textbook, I try to solve it on the screen. In class it would be better, but still we managed to do something here. That it is, right? So that's how we calculate. You calculate work over cycle, and based on this, you will calculate what is gamma. Any question about heat pumps? Do you understand this? So that's what we discuss. And basically in more detail, in fact, many of these things I discussed in my recorded lecture last time, but here we considered it more details, right? We still have several more minutes, and then we also remember that what we proved. We proved that actually, so we have two statements, Kelvin-Plank and Clausius, and remember last time we realized that they're equivalent. We managed to demonstrate it. We managed to obtain it, and we observe that they are equivalent. We prove it. We proved it, right? Remember through this. We demonstrate equivalence. So if Kelvin-Planck statement is violated, then this statement is violated. What is the advantage of knowing gamma? Well, coefficient of performance. Well, that is the measure of your heat pump, how good it is. Because the larger the gamma, the better it works, right? And when you, so basically again, you consider two values. That's what you need if you talk about heat pump. So basically look at heat pump. Look at this equation. So again, in this equation, you have four variables, right? Here you have four variables, and you have two equations, one sign equal and two sign equal. You have this, 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 and this. So if you know two of them, you will find two others. That's what the reason to know gamma. Gamma is a measure of the device. Like I can tell you, why do you need to know that your engine has efficiency of 30%? It's measure how good it is, right? So that is a measure of your heat pump or refrigerator. Okay? Now, so that we considered. So now I believe you know you have basic qualitative understanding of second law. And what you will do next, it will be quantitative understanding, which is more important. Because we should be quantify it. It would be measure. What I tell you, second law tells you what penalty you pay. So we will measure it. Now you know that you should have second reservoir, you should have work input. Now you know that you must to pay some penalty. So here you'll discuss what kind of penalty you are paying. Is it ever possible for QH be larger than QL for refrigeration cycle? In other words, can work ever be negative? Answer is very simple. I think you confuse a little bit. QH is always larger than QL. It is larger. QH is always larger than QL because work input is positive from the point of view of this. QH is work input plus QL. QH is larger than QL. Now, you are saying very good things. What we talk about now, we talk about absolute values. From the point of view of your system, really, you will be right that work is negative. So work is done on the system, it's negative. But when I talk about work over cycle, I talk about absolute value, like module values, okay? So please check your formulas. I think you confuse QH and QL. Vice versa, it cannot be, because what would be vice versa? Vice versa would be that your fridge works for free, which is impossible. Okay, now what we do next, we will talk about how to measure it. And that's the measure of it will be irreversibilities. So now you know that typically the system we talk about, or typically all the process we talk about, most of the process we have in our life, they are irreversible. When you melt sugar in a tea, it dissolves. When you convert heat into work, it's done. It's gone and you cannot get it back. So the process which cannot go backward, we call irreversible. Hypothetical reversible process is when a process can go back to the same trajectory. For instance, if you have frictionless pendulum, the process like this looks like ideally it will be reversible. If you have quasi-steady expansion, piston motion go back and down, it will be reversible. But typically what we always have irreversibilities. We do have irreversibilities. And then you may ask, why do we consider reversible process at all? For two reasons. One reason, we want to see how far you from ideality. Reversible is ideal for you. You want to see how far, how many you from it, how much penalty you pay. And then you will measure how far you are and what are your irreversibilities. So what are some irreversibilities? Irreversibilities, these are non-idealities. They are items which make your process irreversible. Do you understand this? So what are examples? Like if you have heat transfer over finite temperature difference, yes, you cannot convert heat into work entirely, it's irreversible. Unstrained expansion, chemical reactions, spontaneous mixing. If you have, if I have separate oxygen and nitrogen, they get mixed and I have air. Can I get it back? No. Friction. If I have friction, I dissipate, which convert my mechanical effect into friction, right? Into viscous heating. Electrical and magnetic field. Elastic deformation. Typically in the class, I take piece of chalk and crush it into pieces and say I cannot connect it back. It's an inelastic deformation. I crushed crystal structure. All these items are irreversibilities. And later when we talk about entropy, entropy will be a measure of irreversibilities. So you want to know how irreversible the process is. And at this point, when I talk about this, you may see that reversible process is fully idealized. Irreversible is not idealized. And how irreversible you can be. And up to now, you may say this just irreversible, it's not ideal, it's irreversible, and irreversible will be less effective than reversible. Do you understand that irreversible is less effective than reversible because it involves some bad things like dissipation? But if I ask you how irreversible you are, you don't know what to say, right? You cannot be half pregnant, half dead, half alive, right? You may be half health, half smart, but you cannot be half dead or half pregnant, right? So you want some kind of measurement. You want to measure irreversibilities. You want some formula to measure it, right? So that's what we are going to do, and that's what we'll do in the future. And I will finish at this point, but I want to show something like this. I will tell you that there are internally reversible process and externally reversible process, and I show what it is. You know, let's assume I consider a system like this. Let's say I have tank with water. It's closed. And I will take this tank of water into fridge. It gets frozen. Then I will put it on appliance and it gets preheated. Then I will put it to fridge, it gets frozen. Then put it on appliance, it gets preheated. And I can do this 100 times, right? If I am a molecule in this tank, what do I feel? I feel the same process back and forward. So from my point, this process is reversible. But if I'm a guy who moving it back and forward, will I see it? Will I see it reversible? No, because your appliance and your fridge take some effort. So it will be not reversible. We call this process internally reversible. It's internally reversible for a system. And that this process exists in practice. While there are no real reversible processes, there are internally reversible processes in practice, and they're better than internally irreversible. I am stopping at this point. I promise to follow 50 minutes rule. I will stop recording, but I'm ready to. I will pause the lecture, and I'm ready to answer your questions if you have.